Hi guys, welcome back to our discussion on infinite series. So for today's video, we will discuss about series and convergence. So at the end of this lesson, you should be able to understand the definition of a convergent infinite series. So let me start my discussion on the definition of infinite series. So one important application of infinite sequences is in representing infinite summations. So informally, if a sub n is an infinite sequence, then the summation of a sub n, where n is from 1 to infinity, which is the same as a sub 1 plus a sub 2 plus a sub 3 and so on up to plus a sub n plus and so on and so forth, is said to be an infinite series or simply series. The first term of an infinite series is obtained by starting at the value of n as 1. So you get a sub 1. If n is 2, you get a sub 2 as the second term. If n is 3, then you get the third term of the sequence and so on and so forth. So these numbers na a1, a2, a3, and so on, these are called the terms of the series. So for some series, it is convenient to begin the index at n equals 0. But in this notation, we start with n equals 1. You can also start with other integer. As a typesetting convention, it is also common to represent an infinite series as simply summation of a sub n. In such cases, the starting value for the index must be taken from the context of the statement, meaning you have to check the problem first and look for the indicated index in the problem. Okay, next we go to the partial sum of an infinite series. So to find the sum of an infinite series, you have to consider the following sequence of partial sum. So S sub 1 is the sum of the first term of an infinite series. S sub 2 is the sum of the first two terms. Yeah, so you have A1 plus A2. S sub 3 is the sum of the first three terms of an infinite series. So you have A1 plus A2 plus A sub 3, and so on and so forth up to the and partial sum, which is denoted by S sub n, which is equal to a sub 1 plus a sub 2 plus a sub 3 and so on and so forth up to plus a sub n. So if this sequence of partial sums converge, then the series is said to converge and has the sum indicated in the next definition. So by definition, for the infinite series denoted by this notation or symbol, the summation of a sub n, where n is from 1 to infinity, the n partial sum is defined as s sub n equals a sub 1 plus a sub 2 plus and so on and so forth up to plus a sub n. So if the sequence of partial sum denoted by this notation converge to S, then we can say that the series summation of a sub n, where n is from 1 to infinity, converge. And the limit S is called the sum of the series. So we can define S as the sum of the terms of an infinite series from a sub 1 to a sub 2 and so on up to infinity. So the sum of the series denoted by S is simply the summation of a sub n, where n is from 1 to infinity. On the other hand, if the partial sum denoted by, if the sequence of partial sum S sub n diverge, then we can say that the series diverge. Okay, so as an example, this series summation of 1 over 2 to the n, where n is from 1 to infinity, has the following partial sums. So S sub 1, which is the first term of an infinite series, S sub 2 is the sum of the first two terms. So you have 1 half plus 1 fourth is equal to 3 fourths. S sub 3 is the sum of the first three terms of an infinite series. So you have 1 over 1 half plus 1 fourth plus 1 over 8. And when simplified, is equal to 7 over 8. So we can now define the n term or the n partial sum of an infinite series, and this is equal to the sum of the n terms. So you have 1/2 plus 1/4 plus 1/8 and so on and so forth up to plus 1/2 to the n. This is 2 to the n because as you can see, if n is 1, this is 2 to the 1. Then if n is 2, we have 2 squared. If n is 3, then we have 2 cubed and so on and so forth. So based on this partial sum, starting from the first partial sum to third partial sum, um, the sum is has a certain pattern. The numerator is always 1 less than the denominator. So 1/2, same as 3/4. So 3 here is always less than 1 to its denominator. So same as 7/8. And because the denominator are powers of 2, you can write this as 2 to the 1. This is 2 squared. This is 2 cubed. And so on and so forth. So if we want to rewrite the sum of the n partial sum using this pattern. So if 8 is 2 cubed, then the numerator is 1 less than the denominator. So you can write 7 as 2 cubed minus 1, which is 8 minus 1. So in general, you can write the n partial sum as 2 to the n minus 1 because the numerator is always 1 less than the denominator. The denominator is 2 to the n. So therefore, the nth partial sum is defined as 2 to the n minus 1 all over 2 to the n. To determine whether the series converge or diverge, we need to evaluate the limits of the n partial sum. So the limits of the n partial sum is the sum of the infinite series. So by definition, the sum of the series is equal to the limits of the n partial sum as n approaches infinity. But recall that the n partial sum is 2 to the n minus 1 all over 2 to the n. And to evaluate the limits of this n partial sum, we need to replace all the n variable by infinity. Thus, the sum is equal to 2 raised to infinity minus 1 all over 2 raised to infinity. But 2 raised to infinity minus 1 is infinity. Same with 2 raised to infinity. This is also infinity. And the sum is indeterminate, which indicates that we need to apply the L'Hopital's rule to evaluate the limits of the n partial sum. Okay, so we have, by applying L'Hopital's rule, we have to take the differential of the numerator and denominator separately. The differential of 2 to the n minus 1 is 2 to the n times log of 2 to the base e all over. The differential of 2 to the n is also 2 to the n log of e to the base 2. And as you can see here, because the numerator and denominator are equal, so therefore this is equal to 1. And the limits of any constant is always equal to the constant c. So in this case, the limits of 1 as n approaches infinity is equal to 1, which indicates that the series converge and its sum is equal to 1. Another example, suppose you're given the infinite series summation of 1 over n minus 1 over n plus 1, where n is from 1 to infinity. That if the value of n is 1, then you have 1 minus 1 over 1 plus 1 or 1/2. So that's the first term of the series. If n is 2, then we have 1 over 2 minus 1 over 2 plus 1 or 1/3 plus if n is 3, then we have 1 over 3 minus 1 over 3 plus 1 or 1/4 plus and so on and so forth. So in this series, the sum of the first term is equal to 1 minus 1/2. Then S of 2, which is the sum of the first two terms, is 1 minus 1/2 plus 1/2 minus 1/3. S of 3 is 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, which is the sum of the first three terms. So the sum of the n terms or the n partial sum is 1 minus 1/2 plus 1 half minus 1 third plus 1 third minus 1 fourth, and so on and so forth, up to plus 1 over n minus 1 minus 1 over n plus 1 over n minus 1 over n plus 1. And if you look at the terms of the series, you will observe that the inner terms are opposite in sign. Like for example, negative 1 half and 1 half, when added, that's 0. Negative 1 third plus 1 third is also 0. Negative 1 fourth plus 1 fourth is also 0. And before this, there is a negative 1 over n minus 1. When added to positive 1 over n minus 1 is also 0. Same with negative 1 over n plus 1 over n, that's also 0. So, the terms left in the n partial sum are the first and the last term, which is 1 and 1 over n plus 1. Then after that, we need to evaluate the limits of this n partial sum now to find the sum of the infinite series. So we can now define S as the limits of S of n as n approaches infinity. But we obtain that the n partial sum is 1 minus 1 over n plus 1 as n approaches infinity. And if we replace n here by infinity, this is infinity plus 1, and 1 over infinity is 0, and 1 minus 0 is 1. So therefore, S of n, or sorry, the sum of the infinite series is equal to 1, which indicates that this infinite series is convergent, or the series converge and the sum is equal to 1.